from Wednesday's class was taken down. And I got a strike against me because I showed another YouTube video showing people getting hurt on a merry-go-round. So I reposted it last night as 2 parts, and I cut the middle part out. So if you missed Wednesday, you'll miss that. I mean, you can find the real video. Just Google, merry-go-round fails, and those things will show up. I guess that explains why I always have to find that video every time, because I guess it gets taken down. I did my training though. I've also had my videos taken down for swearing before too. It turns out that because they have like some AI in the background that's like listening to what people are saying, and then they've heard me swear, and they're like, this is inappropriate, or it gets tagged as being inappropriate, and then to watch it you have to show them that you're 18 or say you're 18. But okay, so we just finished normal tangent coordinate system. It's kind of different, right? Let me just flash back up to this normal tangent coordinate system, kind of a new way of thinking probably, right? Where we have, usually our coordinate systems are fixed in one location and they're not moving. Here's a case where our coordinate system is moving, right? ET is always tangent to the path. That means our velocity is always in the ET direction. Where's ET pointed? I kind of don't care, right? You just care that it's in the ET direction, okay? I mean, that's it, right? Like, which is it going in the X or the Y? It doesn't matter, right? Because usually we're talking to the forces and stuff don't really matter. In the types of problems we're using this for, it doesn't really matter which direction it's pointed. EN is perpendicular to that, pointed at the instantaneous center of curvature. So in this case, in the bottom left, it's pointed up and to the left, and the upper right is pointed down to the right. So it can move, right? So it's just going like this. That coordinate system is moving around as we're going along, which is kind of new to us, right? New to you. I've been doing this a long time, but kind of new to you that they have this coordinate system that's moving around, right? And so then we went through and defined what velocity is and acceleration is. When we took the derivative of the right, I just said this, the velocity was always just in the ET direction. That's an easy definition. The acceleration, though, you take the derivative of that and then you use the product rule, and it blows up on us a little bit. And we got 2 different parts. We got a change in speed part and a change in direction part to our acceleration, right? And this is the centripetal acceleration, which we demonstrated with the merry-go-round last week, that it's a real acceleration. If you do not, it's kind of weird to think of sometimes, but the change of direction is an acceleration, right? And it's captured by this term right here. Okay, so that was normal tangent coordinates, and we did a couple examples with that. We also talked about how you convert between the 2 coordinate systems. We also did a special case where something's just traveling in a circle, and then we did a couple of examples. I skipped this example, but this is one of those cases where you start out with position and you go to velocity and acceleration. And so in this one, you would take the derivatives. You would take the derivatives of the position and second derivative of the position, and would give you omega and alpha, and then you kind of work your way around with that. And we did that. We just finished this real quick at the end there. Okay. And so today, what we're going to do is we are going to do polar and cylindrical coordinates. Okay, this is our last coordinate system that we're going to deal with, and then we'll do this thing called relative motion. How does one particle's motion relate to another particle's motion? It'll play in a lot throughout this semester, so we'll cover that, and then we're going to kinetics. F equals ma. We're going to start actually right now. Just to recap, we haven't done anything with forces this point. I keep talking about forces, but we haven't done anything with forces. So we need to relate these forces or these accelerations that we're determining back to forces, right? And so a lot of times these equations that we start with, I say, here's the acceleration equation. That equation came from somewhere, and that came from the forces, right? That came from summing forces and setting it equal to mass times acceleration, or work energy and things like that. Okay, I'd like to just connect with you one last time before we go on to the next thing. So polar and cylindrical coordinates, last new coordinate system. I mean, you've done polar coordinates before at some point. At least you should have. At least heard the words before. Okay, so in this case, again, we have a path that our particle is traveling along, right? And we're going to define that in a different coordinate system, okay? There is an x, y coordinate system involved, right? And then there's an origin. And from that origin, we're going to have a vector that points to that particle. Right? It should be pointed right at it. It's kind of my target there. It's pointed right out there. We're going to call that a vector r. Okay? And what we're gonna do is we're gonna have a line keep going in the direction that R was going. That's gonna be one of our coordinates. Right? And then here's our other coordinate. So these coordinates right here, we're gonna call this ER hat. And we'll call this one E theta hat. And kind of at first glance, maybe like, oh, that's just like normal tangent, but it's not, right? In normal tangent coordinate system, you know, we would have had our tangent like that and our normal pointed back like that. That's what normal tangent would look like. So this one's a little bit different. You have this from the origin, you have this position vector R that's just going in the ER direction, and then you have E theta perpendicular to that, okay? I should put in which direction this thing is moving. We'll say that this thing is moving this way. Okay. Theta's getting bigger that way. Right? And so that's our coordinate system. That's how we're going to define accelerations and velocities and positions. So let's write down what these terms are here. ER hat is the radial unit vector. Right. And then E theta hat perpendicular to ER in direction of increasing theta. Okay. Perpendicular to ER in the direction of increasing theta. And so if theta was increasing, going the other direction, E theta would be going in the other direction. Okay? So that's it. I mean, that's it for this course. And again, you'll notice that this is changing, right? As it moves along that path, which the direction that ER is pointing, the direction E theta is pointed, is changes, right? It's going to be right down here, right? Before, down here, ER would be coming out. You'd have another guy going like this, right? And ER would be doing this. And E theta would be doing that. Right? So that's changing again. So when we take the derivative of the ER and E theta, we're going to get some terms. We'll have to go back to that example from before. Okay. So let's do what we've done all these other times. We first define position, then we're going to define velocity, and then acceleration. And this is going to blow up on us a little bit, okay? So the position, that one's easy to define, right? The position vector is just going to be R in the ER direction. Right? Just the way that ER is defined, right? It's just always in the ER direction. So that's the position, R in the ER direction. The R is just the magnitude of that vector that's sticking out, and it's always in the ER direction, just by definition, right? So now we're going to take the derivative of that, and we're going to get velocity. Right? Velocity is equal to dr dt. This is R in the ER direction, dt, right? Apply the product rule. Take the derivative of the first thing, dr dt in the ER direction, plus R times dER dt. Okay? Derivative of the first thing, second thing alone. Leave the first thing alone, take the derivative of the second thing. So again, this is changing, right? My change of, or my my base vector ER changes, right? We just talked about it. We just showed you it's changing. And so we need to, that actually is a term, right? And if you go back to this is going back to that 4 or 5 pages when we talked about taking the derivative of a base vector. We take the derivative of a base vector, it's going to be omega in the other direction. Omega times the other direction. So the derivative of ER with respect to time is just omega times the perpendicular distance, or perpendicular base vector. There's omega in the e theta direction. Okay? So if you take that and you substitute it in, this is what we get, right? Our velocity term now has two terms. Okay? Right? It's going to have an r dot in the ER direction. So if r is getting longer or shorter with respect to time, it's going to be that. It's going to have a component associated with that, r dot in the ER direction. And then when theta is changing, then you're also going to get a velocity term associated with that. Right? And it's just going to be r times omega in the e theta direction. So again, just look back up what I'm talking about there, right? So if I'm talking about the velocity of this component, it's moving along, right? In normal tangent, that velocity was always in the ET direction because ET was always tangent, right? It was always tangent to the path and it was moving like that. Now that's not the case. It's not tangent to the path. And so my velocity term, as it goes along this direction, it's going to have a little bit of e theta and it's going to have a little bit of ER, right? That velocity's headed this way, right? My coordinate system is doing this. And so I pick up two components. I pick up a little bit of a component in the ER direction. I pick up a little bit of a component in the e theta direction. And this is how much it is, right? We can figure out how much of it is in the e theta direction. That's just going to be r times omega. It tells me that it's going that direction. And then is this r getting bigger or smaller? Is the magnitude of this r getting bigger or smaller? And how it's getting bigger or smaller with respect to time is always going to be in the ER direction. Right? So that's what's happening there. So the velocity got a little bit more complicated, right? Because we picked up a couple terms. Yeah.
Why is the position not involving theta? Because on this arc of theta is part of the circle, there are at least two pointing towards the same radius.
Yeah. Yeah, but it's just the way that we were defining it, right?
Okay.
If we're just defining it is you're right. When we try to tie it back to Cartesian coordinates, which we will, right? Like we did last time. There's a way of like saying, okay, well, if I really care which direction it is, let me look back at what it is. Then theta is going to play in. But now ER is just always that way, okay. Right? It's always in the direction of R, basically. So we don't need theta. It gets a little confusing. You'll see there's reasons why we do this, by the way. We'll see in a little bit, like why the hell are we doing this? We'll show you some examples of, it involves merry-go-rounds, okay, of why you would need these things, okay? And then, so you're right, if I'm trying to tie it back to like, if I really care, right? Because you're talking about where, do I really care which direction this is really pointed relative to something else? Then I gotta use theta. And that's when this converting between Cartesian and these coordinates. Okay, so we got position, velocity, now we gotta do acceleration, okay? When we do acceleration, this sucker blows up, okay? Because we're taking the derivative and we have the product rule. So we're taking the derivative of that velocity and we apply that product rule, and this thing is there's a lot of terms going to pop out of it. So acceleration is the derivative of the velocity with respect to time. This is r in the ER hat plus r omega in the e theta hat. All of that with respect to time. Okay? We have to do every one of these terms now. And each one of these is we're gonna get 2 out of each one, right? This one and this one. Oh, actually, this one we're getting 3, right? There's 3 things multiplied by each other. So we have to do the product rule with 3 things. So it'll be derivative of the first thing, leave the next 2 alone, derivative of the second thing, leave the first 2 alone, and just 3 times. Okay. So let's do that. So dr. Oh, I left the dot off right here. I left that dot. dr dot dt in the ER direction, that's derivative of the first thing, plus r dot der hat dt, that's the first term, plus dr dt times omega e theta hat plus r times d omega dt in the e theta direction. And then one more term. I'm going to cheat because I didn't leave myself enough room. And the last one is going to be r times omega times d e theta dt. Okay, and you're blowing up on us a little bit. Okay, I'm just gonna, so that's what we did, right? That's the product rule to that velocity up there. We get that many terms just because of the product rule, okay? And then you can lump like terms and you can make substitutions like with the substitutions and stuff that we had, that we used up above, right? We take the derivative of these base vectors, you use that thing from above there, and what we end up with is this. Okay. So now our acceleration has all of this stuff in it. And you might, again, right, when we were dealing with Cartesian coordinates, things were really easy, right? It was just the derivative of one direction with respect to time in I direction, derivative of the other direction with respect to time in the other direction, right? And there's only those three terms for a 3D problem. This thing blew up on us, right? We've got a lot of things. And again, we're trying to solve merry-go-round problems. This method works out really well, right? And you'll see why it is. And you're like, oh, and there is some overlap between this and normal tangent in certain situations, okay? So that's that. Let's talk about what each of these terms mean, okay? Because they all symbolize some sort of acceleration, okay? There's r double dot. And this r double dot is the radial acceleration. Oh, let's do this actually. I got a little drawing over here. Well, let's tie it to a merry-go-round. Okay, so I've got a merry-go-round. And I've got some origin in there, and I've got a particle that's moving around in it. And I've got my position vector doing this. My coordinates then would be doing this. E r hat, e theta hat. My omega, the way I have it drawn, is doing this. And we'll assume there's an alpha like this. Okay. So again, we're going to picture, honestly, all jokes aside, thinking of a merry-go-round is actually a really good way of defining each of these terms. Okay. So and this is actually too, because let's see, you don't find a lot of merry-go-rounds anymore in parks. Right? You don't, because we saw what happens when you have them, right? People are always getting hurt. The classic one I had as a kid was the one who's a big disc that goes around, and then those like bars on the ends of them as they go around, so that you have something to hit when you're being flown off of it, right? So right, so or it's something to grab on as you spin it, right? That's the classic, right? But hopefully everybody has done this. If not, try to find a merry-go-round so you can experience some of these accelerations. Okay, so the r double dot term is the radial acceleration. That would be say if I'm in the middle, right? Say I'm in the middle and I'm gonna run to the outside. That r double dot would be my acceleration out. It would be the component of me. Right, I'm gonna start shooting out and I'm start running that way. I'm accelerating in the radial direction, right? Sure, the radial direction is turning, it's changing, right? It's not always like as soon as I start, I was going this way, but then a short second later it's this way, and a short second later. But the way we've defined our coordinate system, it doesn't matter that that's changing. And so it's my acceleration out from the center, or my deceleration, right? If I was running to the outside and I tried to stop myself, that's that r double dot term. Okay, and that's great. I get that one. Okay. Okay. R omega squared term. What's this term? You should know that one. We just did that one last time. Mark, you got with it? Remember, you got this one right last time. Yeah, that's good. Good. Whoever whispered that to Mark, thank you. Is that Riley? Is that you, Riley? Thank you. This is centripetal. Yes, it was teamwork. Don't do that on the exam. Don't help on the exam. So that's the centripetal acceleration, which there should be that component, right? That as as you're going, like, say I'm that person out at that particle right there, and as I'm rotating it around, I better be accelerating back to the middle. If I'm not accelerating back to the middle, then I'm flying off, right? Which we saw just last week, right? Next time, I did learn, I had to take some training on YouTube, that I can put images of kids getting hurt if I say you shouldn't do this, right? But I did say that, like, I appealed it and everything. It's like I said, remember I said, don't do this, but I need to make it more clear of, like, look, I'm gonna show you some dangerous acts. Definitely don't do those, right? But I've learned that in the training, and then I have to say something in the statement. But that I better be accelerating back to the middle. So say I'm not even moving, right? I'm just standing out there and this thing's whipping around. I better be applying a force back to the middle. If I'm not applying a force back to the middle, then I can't accelerate back to the middle, which I take off on a tangent. So that would be, in your mind, think yourself being on a merry-go-round, you're standing in one position, that would be the leaning back to the middle and planting your feet, because that's what's gonna keep you accelerating back to the middle, right? That's the centripetal acceleration, so that has to be there as well, right? By the way, both of these are happening at the same time, right? Both of these are happening at the same time, and you can see both of those ones I just talked about are in the ER direction, right? So if I'm standing at that position, I'm leaning back in the ER direction. It's a negative here too. It's a negative R omega squared. So I'm leaning back opposite of the ER direction, and that's that direction. If I'm sprinting out, that is in the ER direction. Yes, sir.
Sometimes in like physics and dynamics problems, it's useful to move the coordinate axis around. Is that something we're gonna have to do in non-Cartesian?
Like where the base is at and stuff?
Yeah.
No. It ends up being easier than that, right? Because like if someone's in a merry-go-round, I wouldn't want to put this thing out here someplace, right? Because then it'd be weird. So don't worry about that too much. It's usually pretty obvious where that base one's at. Okay, so triple acceleration. So those are both in the ER direction. There's also going to be some acceleration in the E theta direction. So let's talk about the accelerations in the E theta direction, right? The R alpha term, all right, this is, what do we call this? This is tangential acceleration. Oop, not tangential celebrations. Okay, tangential accelerations. This one too is okay, right? So say I'm standing at that fixed position and somebody's on the side going this, right? Whipping it, right? Getting it going. Or put the motorcycle on the side, put the wheel on it and gun it, right? That's, you're increasing in alpha, right? Your omega is getting bigger. It starts at, right? The velocity, the angular velocity is going from one angular velocity to a higher angular velocity. So there's acceleration associated with that. That's alpha. And if I take R times alpha, that tells me what that acceleration is. So as I'm standing on there, if somebody starts increasing alpha, somebody starts with they crank that motorcycle, right? It's gonna speed me up, and I'm gonna, I have a tendency to kind of want to fall back, so I have to lean forward. I have to apply a force forward to keep myself going and accelerating in that direction, right? Otherwise, they want to whip out from underneath me, right? So that's one you can envision as well. You can absolutely envision that tangential acceleration, right? Because if there's a change in velocity, there has to be a change in there's got to be acceleration if there's a change in velocity. The last one, though, is a little less clear. That's a 2r dot omega. Okay, that's the last acceleration we talk about. Anybody have a guess on what this one is? I know you've heard of it. Okay, I know you've heard of it. It involves this, right? If I'm in the middle, or just envision yourself back as a young child, right? Long time ago for me, not so long ago for you. You guys are all born in 2000s, right? Yeah, fuck all you guys. I graduated from college in 2000. Again, let me still think I'm one of you guys. Okay, but as a young child, taking a step right out, and then taking another step out. What's something you feel when you do that? Right? Do you remember this? You feel like a sideways, like you feel like dizzy, and you start like you're walking along, and then you're kind of like tipping over as you're walking. Do you guys remember this?
Sure. Centrifugal effect.
No, centripetal is the stuff back to the middle. This is it's you're on your it starts with this C. It's Coriolis, you did it. Yeah, the Coriolis effect. That's what you feel. You ever heard of the Coriolis? Right? Ever heard of the Coriolis? That's the Coriolis. We got it. It's right here. It's right here, right? We proved that it's there. And what this one's associated with, right? This one's associated with is I'm in the middle, right? And actually, right in the middle, I have no velocity in the e theta direction, right? Velocity in the e theta direction is r times omega, right? Yeah, in the e theta direction, right in the middle is r times omega. In the middle, r is 0, right? So I have as I'm standing in the middle, I got nothing. I have no e theta velocity. But as soon as I take a step out, I go from no tangential or no e theta velocity, I gotta speed up, right? Because my r has gotten bigger, right? And so I've now picked up a velocity in the e theta direction. But if I just take one step, now I've sped up. Now I'm going that speed. Now I'm going r omega at that new r. I wouldn't feel it anymore, right? I would just take one step and then it'd be gone because I've already once I accelerate to that new radius, then I'm okay. If I take another step out though, I'm going from a slower r omega to a bigger r omega because my r got bigger. And so every time I take a step out, I will pick up lateral acceleration. I have to speed up. I'm at one level. Right? I'm at one level, and every time I take a step out, I have to get faster and faster to the left, right? Every step out, right? And as long as you're not moving, then you wouldn't feel that. And, well, look at this. It's a function of the velocity, right? So if the velocity towards the outside isn't there, then you don't get it. But if you have a velocity towards the outside, then you get it, right? So that's the Coriolis effect, right? Where it plays in, and where you may have heard of it before, is in toilets. Have you ever heard of this before? Coriolis. They say, at least the old saying is that in the southern hemisphere, the toilets swirl one direction, and the northern hemisphere, the toilets swirl the other direction. It's not true. I mean, it is true, except for it's just because of plumbing. The Coriolis is not so right, because the Earth is a disk, if you believe in this thing, is a disk spinning around, right? And it spins faster at the equator than it does up at the top, right? That would be, here's your, one of the poles. Here we are at the pole, and there's the equator down there. It's traveling faster. And so as you move around on the Earth, you get this. And then the opposite would be true if you're underneath looking up at it. Your Coriolis would be acting in the opposite direction if you're underneath looking up at it. Again, if you believe in this sort of thing. Okay, but so then it doesn't necessarily work for toilets. I guess I heard that if you go down to the equator, some country in the equator, there'll be a guy there, and he's got a funnel, and he's got like a toothpick, and he goes on one side of the equator, and it says, look, it's spinning this direction, and then he goes down on the other side, and then of the equator, it says, oh, look, it's spinning the other direction. It's not true. It's the Coriolis effect at that. He's just tricking you. If anybody has a doubt, call him out. Say, you're just tricking us. But it's not big enough. The effect isn't big enough on the global scale. What it is big enough for is storms, right? So you may have heard that like on the northern hemisphere, you have your hurricanes spin one direction, and the southern hemisphere, they spin the other direction. And that is true. That is actually something that happens. They also call them different. They call hurricanes in the northern hemisphere, and oh, you're a southern hemisphere guy. What do you call those things? Huh?
Hurricanes?
You do call them hurricanes.
I didn't know.
Is it cyclone? Not cyclones. What is it? Typhoons. Now you still call them.
Asia.
More Asia calls them typhoons. Okay. Yeah. So are you missing out on any skiing or anything right now? Are you a skier?
No, it doesn't snow where I'm from.
Oh, it doesn't. Okay.
Very hot.
Yeah, you'll get it here soon. Yeah. Okay. So those are the things. I got a little video that talks about the Coriolis and how it affects. The other place that you have to take into consideration the Coriolis effect is intercontinental ballistics. So if you're mechanical engineers, you might have to, right? So you got intercontinental ballistics. You better take into consideration that the Earth is spinning in that time. Okay. So another YouTube. It is Friday after this. This is a 2-minute video talking about the storms. The one that I usually reference is missing, so we'll see how this one is. This is a 2-minute description. Hopefully it looks.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you, but if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low-pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise, and that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving this example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video, and that's kind of the point. I hope you got what you came for. And the Coriolis effect doesn't really influence toilets, they're just really too small, and the direction of the spin more depends on the placement of jets inside the toilet. But that's it, that's the Coriolis effect.
That's what I just said! Oh man, look at me. It's the plumbing. They do spin the other direction. It's just because they're weird down there. Did you ever check it out? Check it out next time you're in Australia. See if your toilet's spinning opposite of our toilets. Call your mom tonight. See, hey mom, could you go take a video of the toilet and then maybe? Cause I'll show it on class if your mom takes a video of the toilet. Okay? right? And then you can do our toilets. That'd be great. Okay. All right. So here it is, right? So let's talk about a special case, just like we did with normal tangent, right? So this is what it looks like in its purest form, right? It is this, right? So this is all of these things. A lot of times, we'll see in examples, a lot of times some of these terms just go away, right? Like if we'll look at a case right now. If something's traveling in a circle, a lot of these terms will just go away and things simplify down, right? So in the case where something's traveling in a circle, right, r dot is going to be equal to 0, and r double dot is equal to 0, right? Because if it's traveling in a circle, then that radius is not getting any bigger or smaller. If the radius isn't getting bigger or smaller, then you have no velocity in the r direction, and you have no r double dot. You have no acceleration in that direction either, so you get two of those things are 0. And so really, you just go back up to this, and you just cross out the r double dot, and you cross out the r dot. So you lose your radial acceleration, and you lose your Coriolis, right? And when you do that, also this thing is that radius, just kind of show it over here, right? Your radius ends up being fixed. And if we called that radius capital R, right? And again, our ER would be doing this. and E theta would be doing this. Just to show it what those coordinates look like on that circle. And again, right, you wouldn't be, R is fixed, and so there would be no derivative of it, or second derivative. There would be, but they'd just be equal to 0, right? So my velocity just becomes R omega in the E theta direction, all right? And my acceleration just becomes you just have the centripetal acceleration and the tangential acceleration, right? And that is pretty dang close to what we had for normal tangent coordinate systems, right? If we flash back up to the normal tangent coordinate system, we have the special case of a circle. Right here, right? It was R omega in the ET direction plus R omega squared in the EN direction and R alpha in the ET direction. And so they're the same thing, right? So you know, because at that point, when it's traveling in a circle, those coordinates line up, right? If we were talking normal tangent, my tangent would be doing that. And then actually the one thing that would be different, my tangent would be going this way and my normal would be going this way. So there's a little bit of difference on the circle because the normal is pointed back to the middle in this case, whereas my radial is pointed out away from the middle. And so the only difference between those two when it's traveling in a circle is we pick up a negative in our ER direction. It's a positive in the normal tangent direction. And the reason I spend so much time is because you're going to have some problems in your homework where you could solve them either way. You could do polar coordinates or you could do normal tangent, especially if something's traveling in a circle. Go for it. Do whichever method you want to use. It's just the only difference is one's going to be a negative E in the ER direction, the other one's negative in the ER direction, the other one's positive in the EN direction. Other than that, they line up. They line up and they're the same, which it should be. Okay, right? So then you might be asking yourself, well, how come I can't use normal tangent to solve the merry-go-round problem? And it has to do with, if you think about it, the EN and the ER direction. I guess also just think if I was a person on this merry-go-round and I was walking to the outside, if you think about what the path that person actually is taking, the path that person is taking is like this. It's a spiral going out, right? And so if you were trying to track normals and tangents as this thing was like moving out, it would get too complicated, right? It would be really hard to try to trace that because again, the tangent is always perpendicular to that path, and the normal point it would just get out of hand. And so if you're doing something where you have radiuses changing and stuff like that, you got to use polar coordinates. Okay, so to turn it into 3D. Right, we would do they call cylindrical coordinates, right? You can actually turn normal tangent into cylindrical coordinates as well, right? But all you simply do when you have cylindrical coordinates is you just add in a z component, right? My position, that's all I've done right here, right? My position just becomes this, right? It's just r in the ER direction plus z in the k direction. Right? And that's how we get this thing, and this now would be a 3D problem. We could talk about things moving in the z direction as well, because you're going to have some homeworks that involve this as well. My velocity, we just add in the derivative of z, right? This is my velocity in the z direction. So these guys are just kind of what we derived a few minutes ago. We just add in velocity in the k direction, right? So you're going to have stuff, it'd be like the merry-go-round traveling like this, merry-go-round traveling like this, and that's what the ER and E theta direction is. And then we just coming out of the board would be the Z direction. And so you could imagine, also having a direction that way as well. Example there would be like if I had a ball on a string and I was whipping it around like this direction, holding this. If I was going really slow, then it would kind of slack down a little bit. If I sped it up a little bit, it would kind of want to move up that direction. And so that'd be an example of something that would have like a third dimension to it. And then accelerations, again, same accelerations that we just derived, but then we just take the derivative of the velocity in that direction, z double dot in the k direction. Okay? So we're going to do a couple problems where we have to have that component as well. Okay, and then just like we did with the other method, normal tangent coordinate system, we can also convert between the two, and it just involves the same kind of geometry, trigonometry, if you will, too, right? You just go back to this if you go back to this, right, you can figure out what component, how much this goes in the y direction and how much is in, or the x direction, and how much is in the y direction, how much is in the x direction, how much is in the y direction. So you can kind of break those things into its components in terms of normal tangent, and it's pretty simple derivation, and you can come up with this, right? So if I really do care, back to your question earlier, if I really do, or someone's question earlier about, do I care what the theta, there it comes in. That's where the theta comes in right there, is if you're trying to do that. And the reason you do this a lot of times is if you're trying to compare two different particles on two different paths, then you really need to know how do they relate to each other, and in order to do that, you have to put them both in the same coordinate system first, okay? All right. Okay, let's do this one really quick. Merry-go-round is spinning with a constant omega. You start to walk the outside with an r dot. This is a super easy one. And it's just kind of identifying what the different components are. In the middle, walk it to the outside. My acceleration, it says, what is the acceleration? Well, the acceleration, just write it down, r double dot minus r omega squared, that whole quantity in the ER direction, plus r alpha plus 2r dot omega in the E theta direction. Okay. And so this one says you start out with a constant r dot. That means if r dot is constant, then r double dot is 0. Right? That's what they told us. So if that's constant, you take the derivative of a constant, you get 0. Right? And then it has a constant omega, which means alpha is equal to 0 as well. Our omega is constant. That means alpha equals 0. Right? So then you just cross out those terms. There's my acceleration. Negative r omega squared in the ER direction plus 2r dot omega in the E theta direction. I don't know why I have that example. That's pretty easy. Okay. But I mean, that just kind of shows you that. So if I was that person in the middle, and instead of accelerating out to the outside, I just am slow, have the constant velocity walking to the outside. Then if that's the case, and omega is constant, so there is no person speeding me up, or there's no deceleration from friction or whatever, then all I would feel, the only acceleration I would feel, I would have to be having a centripetal acceleration in the ER direction. So as I'm walking out, I'd have to be kind of leaning back, so I'm kind of accelerating back towards the middle a little bit. And then also I'd be feeling that Coriolis. So I'd be feeling this kind of like wanting to tip me over as I was walking to the outside. That's all I would feel. And I wouldn't pick up any of the other stuff. And again, what's really crazy is that all of these things are happening at the same time, right? If I was sprinting to the outside, I would have an acceleration to the outside, but at the same time, I would have to be accelerating back towards the middle, otherwise I'm flying off, right? So those are both in the ER direction. And the same thing in the lateral direction. As I was walking to the outside, I'd be feeling the Coriolis, but then also, if there was an alpha, I would be feeling that alpha as well. They compound. They're all acting in the same directions and stuff. So, cool. We'll save this one for Monday. Cool. Now I'm going to assign another homework this afternoon, okay? And that'll be on, it's a little bit longer one, so if you can get started, we've covered almost everything you need to do that next homework, right? And I think there's like 9 problems on that one. I think there's three Cartesians. No, there's not. There's three normal tangents, 3 polar coordinates, 3 relative velocities, which we're going to cover on Monday. So get started on it. Don't wait till the last second. Good luck on your homework that's due tonight. Have a good weekend.